So today I will be talking about something called half metallic ferromagnets. In short, HMF. Now, these materials are the main components of area of study called spintronics. Spintronics, as you can see from the name, it usually mm, is a study which uses the spin degree of freedom of the electrons, and there are many spintronic devices which are being proposed, and it may take over electronics in the coming years. The devices are pretty much highly efficient devices compared to what we have, the microelectronic or the nanoelectronic devices that we have presently right now. Now let us come to HMFs first. Now the word half metallic means that uh, the band structure is different from metals and also semiconductors. It's not an insulator, of course, but it is neither a metal nor a semiconductor. And you can see like that it has two channels, out of which one is conducting, one conducting for one spin, and the second one is semiconducting for the second spin. So there are two spins forming two channels, one is conducting and another one is semiconducting. Now coming to the density of states diagram, semiconductor diagram, typical semiconductor diagram will be like this with the valence band and the conduction band. So there will be an upspin here and a downspin here and an upspin here and a downspin here. This is for a semiconductor. Whereas in case of metals, as you know that there is no band gap, so the bands overlap, so we can draw it like this, up down, out of which, so this is for a metal, this is of course is the Fermi level, that is the Fermi level, and in the metal this lower portion is totally filled up, and this is actually a non-magnetic metal. there are no unpaired electrons. Now, what happens in an uh, half metallic ferromagnet is, as you can see, that it is a hybrid between a semiconductor and a metal. So it will look, the band structure or the density of states will look something like this. So the first part, one of the parts will be exactly like the metal one, whereas the other part would be like the semiconductor one with the band gap. This is again the Fermi level, and this is for half metallic ferromagnets, density of states. So this is conducting channel for one spin, so this one is conducting, and whereas this part is semiconducting. Now, what are the materials that are actually half ferromagnets? So half ferromagnets properties are basically shown by magnetic oxides, then you have dilute magnetic uh, 3,5 compounds, then you have vascular alloys, so these are the materials which actually are half magnetic ferromagnets. Now, it is also called a semi-metal, and it has got very small overlap between the bottom of conduction band and top of valence band. And also there is no band gap and negligible density of states at Fermi level. So at Fermi level there is no band gap and negligible or very less negligible density of states. Now if you compare the band diagram once again, so if you plot energy here, so and if you plot the EF here, so this is how a metal will look like. This is fully filled. This is below EF, it is fully filled, and above EF it's empty. So this is for a metal. For a semi-metal again, it will be like this. So as we have said, very small band gap and absolutely no density of states at one level. This is for a semi-metal. And coming to semiconductors, so for a p-type, with the Fermi level close to the valence band, and this is for an n-type. The Fermi level close to the conduction band, and of course the insulator where there is a wide band gap. This is for an insulator. Now, although we have mentioned semi-metal, HMFs are not exactly a semi-metal. That is because, as you can see, what we have drawn here, this is how the density of states of semi-metal will look like, whereas this is how the density of states of a half metal magnetic ferromagnet or half metal ferromagnet will look like. So this is a semi-metal. There is a basic difference. It is actually a hybrid of a semiconductor and a metal, whereas this is totally a different case where there is no band gap or density of states at the Fermi level. So these two are different. Now, HMFs are substance that acts as a conductor to electrons of one spin, an insulator or a semiconductor to those of the opposite spin. Now, the valence band for one spin orientation is partially filled, while gap is in the density of states of the spin. So let us now try to understand what will happen if there is a surface magnetism associated with this half metallic ferromagnets. Now, when we apply a magnetic field in the z direction, now the electrons or the energy of the electrons with spins parallel to the z direction, they get raised to an energy UBH, whereas those electrons which are anti-parallel, I mean they are parallel but in the opposite direction, they get decreased by the energy UBH. So let me put here a minus sign is equal to minus mu BH, and this is basically a very well-known phenomena of Zeeman splitting. So the band gap will look something like this. So this is your EF. So this will go down, those which are antiparallel, this will go down, and this one will go up. Okay. Now, apart from this, after this has happened, so what also happens is that there is some transition taking place between these two states. That means those electrons which has gone up, they actually come down to the other state. So we can actually represent this one as the number this is the number of electrons which are initially present in the spin-up state. They actually move down to spin down state. It means this one, this transition that we talked about, this one, we're talking about this one. Now, due to this, due to this phenomena, this is the reason that the system starts to behave as a magnet. System exhibits magnetization. And the magnetic susceptibility is given as two mu b square rho EF. This is the density of states, and this is called Pauli's paramagnetic susceptibility. Now, if there is an exchange coupling of electrons between those two states, so if exchange coupling takes place, then the susceptibility is given as sorry, this is rho. It's not this factor I rho f. This is called the Stoner enhancement factor. Stoner's enhancement factor. And this factor is proportional to the density of states at the Fermi level. So it depends upon the DOS, density of states at Fermi level, and it is large when we are talking about surfaces. So large at surfaces. In fact, it is not only one rho. It is basically this is basically is the Stoner's factor. This whole quantity. So the 2 rho E density of states gets multiplied by the Stoner's factor. Now, so the conclusion is the system which is paramagnetic in bulk, because of the variations of the electronic structure, it becomes ferromagnetic at the surface. So let's put it in this way. In bulk, it is paramag, and it transforms to, when it goes to the surface, it transforms into a ferromagnetic material due to the electronic structure of the material.